I would now like to welcome up our next speaker, John O'Sullivan, for the talk, Accelerating Geothermal Modelling with Cloud Computing. Please welcome up John.
Kia ora everyone, I'm John O'Sullivan from the Geothermal Institute. So I'm going to give you some background first about who we are and then I'll talk a little bit about what we do, and then I'm going to talk about the tools we use, and then I'll talk about HPC, and then cloud computing, and then talk about the future. Apologies, you probably don't really want to know about necessarily geothermal modelling, but none of the e-science stuff will make sense unless you know a little bit about what we do. So we're at the University of Auckland, and we have been established for nearly 50 years. I'm 4 years older than the Geothermal Institute, so we're both celebrating 50th birthday soon. And we do teaching, research, education, and we do a lot of commercial consulting around geothermal modelling applications and other geothermal applications as well. I lead it with Associate Professor Sadiq Zarouk, and it's a real focus on education, knowledge transfer, capacity building. That's a bunch of our students there. They come from all over the world, particularly Indonesia, the Philippines, East Africa, Central South America, as well as New Zealand, of course. And we've got over 1,800 graduates over the last 40 years, and a lot of them are now very senior or even retired senior management in international geothermal companies and institutes. So we've got they're a great asset, those graduates, and they advocate strongly for our research and teaching approach. We spend a lot of time sort of building really strong relationships with our key stakeholders, our partnerships with GNS and Sequent, and also Contact Energy and a lot of our other people that I'll mention. And a big part of it is, we're doing this to contribute to sustainable development. Geothermal's got a really important role to play in a just and a sustainable energy transition. So we're thinking about it not just from an economic power generation point of view, but environmental, social, cultural, and really long-term intergenerational sustainability. So what do we do? My team does geothermal modelling, and we use physics-based models, big finite volume models, to represent what's going on underneath the earth and in these geothermal systems. You can think of them like any physics-based model are basically simple digital twins. So at the top, we've got a picture of a conceptual understanding of how Wairaki geothermal system works. It's hot water that convects around, and you get steam in different parts of the subsurface. You drill wells into it, and up the well travels the steam, and you can generate turbines with it, right? And turn turbines with the steam and make power. You can also use the hot water for all kinds of other applications, drying milk and drying timber and making green hydrogen, truly green hydrogen. And then you need to put the water back down, and you need models to understand how this all works and how it's going to be sustainable in the future. So, that's an example of the same this is a vertical cross-section through Wairaki. That's Mount Tauhara, the little grey blob, and Lake Taupo is sort of in front of us. And then beneath it is our finite volume representation of the temperature distribution and the flows, subsurface flows of steam and heat in Wairaki that we use for forecasting. So the idea is you try to take a limited data set, understand the behaviour with your model, reproduce the behaviour you have historically, so that you can forecast forward and give advice about how to use that energy and how to manage it. So we have all kinds of projects. We've been working on Wairaki since 1985, so that's one of our really long, enduring relationships. But we have lots of student projects and lots of research and commercial projects, and because these are supporting building power plants and getting financing for that. The outputs of our models, they go to support sort of hundreds of millions of dollars of infrastructure investment. And this is, again, the sort of thing that we look at. I didn't have time to put a nice movie of watching the steam sort of move around and bubble, but we're looking at forecasting where it's hot and where the steam is and how it moves. The white lines are the wells, so they drill 2-3 kilometers into the earth to get the steam out of the right place. And it's multi-phase, multi-component chemistry. There's all kinds of complexity in the underlying physics models, okay? So these are complex models to solve. So back in, up until about 2014, the industry standard was a serial code called TUF2. It came from TUF1 or TUF, and the algorithm's about 40 years old, right? And so it's a robust algorithm, but it ran on a serial computer and was pretty slow. It gives you an idea of how good the algorithm was. It was still being used after 30, 40 years, but it was slow. We got a grant with GNS to develop a modern code, and ran from 2014 through to 2021, and it was officially released in 2019. It's called Waiwera, which means hot water for New Zealanders, for people who don't know Te Reo at all. And it's based on PETSI, which is a library of parallel coding out of Argonne National Labs in the US. We've now used that on lots of projects. And it's a standard sort of parallel code. It's running domain decomposition to sort of solve these massive physics-based models on lots of different processes at once, and uses MPI to do all of that. So we've been using it on a lot of our commercial projects now since 2019. Even in 2017, sort of in the proof of concept stage, we were already using our commercial projects to help with the development. And the key idea was that we didn't change the algorithm, we just changed, so it's the same, it was designed to replace this industry standard code, and it's been very successful in that. So when we were developing it, initially we used small HPCs, 10, 20 CPU cores on them. And then with a lot of help from the NESI team over sort of 2015 through to 2017, we got it all up and running on Maui, and that was a real game changer. We had that process going, and we got orders of magnitude speed up on these simulations. Pretty small there, but you're looking at 25,000 seconds to run it on a computer, down to sort of 400 seconds for the same simulation on a single core. And they look like sort of small models, but this is an industry standard size model, because the industry standard is used to those 23,000 seconds, which I forget what it is. It's whatever it is, 8 hours or something. And you can see, because the physics is complicated, right? So you can see that the scaling sort of tails off fairly quickly around 10 for this, because it's actually not that big a model, but the physics is complicated, so that's why it's slow. And doing that on Maui with NESI, that completely changed the way we do geothermal modeling. So suddenly, instead of setting a model going and waiting 8 hours and forgetting what you were doing and coming back the next day, having to remind yourself and then maybe change something and, oh, that wasn't right. We were getting answers in a matter of minutes. It meant we could run bigger, better, much more high fidelity models. So this is an example of one which is about 3 million blocks. So, almost 2 orders of magnitude than an industry standard. And it meant that we could do things suddenly, instead of people saying, oh, it's a 6-month project to see, well, how should we change things? We started to be able to do things operationally. And so we were giving quarterly results quarterly forecasts to our clients, because we could turn it around that much faster because of running our models on Maui. And we started to be able to do uncertainty quantification, which, 8 years ago was impossible, and now it became possible. So it completely changed how we do geothermal modelling now. So then the next thing that happened was we thought we'd better try doing it in the cloud. That actually largely happened because of a good friend of mine works at AWS, and he said, you should talk to my guys and we should see what we could do. And we had actually tried it on AWS in the early days and found that it worked well on a single node, but the interconnects meant that we couldn't scale it. But then in 2022, we did a lot of work with the AWS team, and they helped us to create a virtual compute cluster. And the key was the fast FSX storage. That meant that we could run multi-node, parallel simulations that were really efficient. And they were running, we now, in 2022, we saw that they were outperforming what we were getting on Maui. So that's just been the next sort of game changer. And then here's just some results, really just showing, again, really good scalability. This is a slightly bigger model, so it sort of scales up to about more sort of 40, 50 nodes, 40, 50 cores, sorry. And yeah, and just, you see it's just about, the performance is comparable, but definitely outperforming Maui at this stage. And so I guess the takeaway for us is that, so the HPCs with support of NESI, that really changed how we do geothermal modeling. But now being able to do it on the cloud with these sorts of efficiencies, it changed us how we do the projects altogether. So now our partners, our clients, they're really expecting that we will do uncertainty quantification on every project because we can run 5,000 models in an afternoon on AWS because we don't have to worry about queues or anything like that. We spin up our cluster and we send off the jobs and we get the results we want. The other thing we've been able to do is let clients take control of their own projects and send their own simulations up for forecasts, which was also really a big change. Because we can control what the configuration of our clusters are, we can have specialized pre and post processing nodes, and that means we're not moving so much stuff around because we can use the appropriate tools on the cluster for doing the different jobs. And the other thing that has been really great is that some of our clients are in Indonesia and there's issues with data security and they aren't allowed anything to go to the US, and so being able to spin up an Indonesian cluster has been critical for being able to deliver a solution for them. This is how we do it. I don't have a lot to do with the setup. It was largely done with a lot of support from Todd Churchwood and his team, and guys in our team, Ken Deckers, who takes care of this. But basically, the key is the parallel cluster manager configuring, and the fast local FSX storage are the key. And we've been using the HPC 6A compute nodes, which are in US East 2 zone. And then what's nice now, post-COVID, we've got some of our team in Auckland, some of our team in New Caledonia. One of them's married to a human rights lawyer, and they've been in DRC. So, being able to connect remotely and using remote desktops to connect has been really powerful as well. So where do we go to from here? Having this power to do really robust, genuine uncertainty quantification, of course, then what happens is your scientists start saying, but maybe we were completely wrong about what it looks like underneath, and could we do a whole other possibility sort of search? So that's possible. Obviously, as soon as you start saying we can do this, people go, whoa, well then maybe we could do this as well. And probably a lot of you will tell you I told you so, but 5 years ago I would have said these physics-based models aren't appropriate for machine learning, and when we started running thousands and thousands of them on Amazon and looking at the results, I started saying, oh, some of those are better than my calibration. So it turns out I was wrong, and probably some machine learning model calibration for these physics-based models is definitely on the cards. We're looking at extending that idea of running people's models or them interacting with the models to send them up to a fully hosted service where we would just look after them and we wouldn't necessarily be in charge of the models at all. This all sort of then opens up the idea of, fully sort of automatic calibration, digital twins, live updates online. And we're also talking with AWS about how to optimize our code for new and different cloud architecture with different processes and things coming through. So, the takeaways are like the modeling is, I know, again, probably preaching to the converted here, but modeling and e-science is a really integral part of geothermal developments and management of geothermal resources, especially if we want to do this as sustainably and fairly as possible. HPCs, using Waipapa on HPCs fundamentally changed the way we do geothermal modeling, and that has just been an absolute revolution. And now moving it into the cloud has just completely changed the way we do the whole projects. So we're still, we've got an ongoing relationship with NESI to keep, then they provide invaluable support for doing that research and looking at improving the underlying physics models and proof of concept. And the flexibility, scalability, and power of AWS's cloud computing, it just unlocks huge potential for what we can do next with all of this in geothermal modelling. Tēnā koutou katoa, thank you. And I just really want to acknowledge the support from AWS and from NESI, also from Sequent and to MB for their support for developing Waipapa. Thank you.
Thank you very much, John. Are there any questions from the audience? Yes.
Really good talk. I love those kinds of talks. A couple of years ago, I think we extended Mahuika, and we now have Mahuika extension, which has better processors. So this might actually be an architecture you want to try it. You code on. You get many more cores per node, so you can run on one node typically, because we have 128 cores per node, and AMD processor. So just something to try out and see how your code performs, and let us know if what the performance is compared to Maui.
Yeah, that would be great. That would be great, because I think that was one of the things that we found, being able to go up to 96 cores on those HPC 6A was a big step from the 40 cores previously on Mahuika. So yeah, that would be really keen, and we will try that. Thank you.
John?
All right, thank you.
And I would now like to welcome up our next speaker, Guillem de Valles, with the talk Bridging the Gap with OpenOnDemand. Please welcome Guillem.
Kia ora, ko Guillem de Valles toko ingoa no eRangahau. And I apologize about this bad material pronunciation. I assure you that the rest will be badly pronounced in English. So I work for HPCNow. You will see the logo in all the slides. And in HPCNow, we provide advanced supercomputing services for science and engineering. And we cover multiple areas, such as cluster design, HPC administration, and user support. That is the area that I work on. And today, I'm going to talk a little bit about OpenOnDemand. I think that there has been a talk yesterday about that. If you attended that one, you can have a quick nap. So OpenOnDemand, it's an interactive HPC access via the web. And it provides easy-to-use, web-based access to supercomputers, allowing it to use in an intuitive and interactive way. Some features include access to the HPC, to a huge performance cluster, one cluster or more, plugin-free web experience, easy file management. You have also command line shell access, Also, you can manage your jobs, monitor them, submitting them, cancel them, whatever you want. And it provides graphical desktop environments and applications, and some of these applications are applications that are widely used, like Jupyter Notebooks, Visual Studio Code, RStudio, etc. So it requires zero installation. You just need a browser. You can run it from your browser. And it's very easy to use. You only have to provide a username and a password, and you can start computing, launching jobs, and so on. Interestingly, it's compatible with any devices. You can run it in a laptop, but you can also run it in a mobile phone, tablet. But I have tried it on a mobile phone. I don't recommend that, but do it on your own. And one of the best characteristics is that it lowers the barrier to entry. There are lots of people that I have been working during my career, I will say especially clinicians, that you put them in front of a shell terminal and they start sweating, they cry, they run away. So this is a way to use an HPC that doesn't require this deep, or let's say, more informatic knowledge. It's also free and open source, and very configurable and flexible thanks to it being open source. So you can configure it totally to meet your users or your clients' needs. Here I have a short demonstration video. So as you see, you just need a browser, you put your username and password, and you get in this page that you get your pin apps. You can see different apps here. And it allows you to do normal file operations that you will do in a normal graphical interface. But also, interestingly, it has shell access if you want it. You can use it as a normal shell. And all of this is inside already an HPC. So you can create files, both from the terminal, or you can create them also in, well, if you create it in the terminal, it will appear here. You can also create the files from the graphical interface. You can move these files, you can create folders, you can delete folders, whatever you can do in a normal file operation management. Now it comes a part of the video that I always struggle a little. Interestingly, also it comes with a text editor that you can choose different languages, even different themes, and all of this is from the same web page without having to change or to open anything else. And here you can compose jobs that they will be launched in the cluster. You can select all the things that you want in a job independently of the workload manager that you use. And simply, here it's a very simple job. You can compose it, change all the characteristics of the job that you want, and launch it, even job arrays. You can also manage your jobs, check if the job is running. If it's not, you can cancel it. You can also check the output of the jobs. You can do lots of operations here. The video goes a little bit fast because it was very long and I had to compress it to fit into the presentation, so it's a little bit going all over the place. But as you can see, you can pass different, this is to get, for example, a job that will run this, and you can check the output outside. Sorry, it's a little bit going too fast. You can check, as I was saying, both the output, the logs, really what you can do from a shell access, well, from a terminal, you can do it here. So it's quite powerful. Here it's a little bit showing the different jobs, if they are submitted or not. And also, through different apps, you can monitor these jobs even in using graphical interfaces like Grafana or Kibana or whatever you use to monitor your jobs in the cluster. Interestingly, you can also start interactive sessions, so not just bad jobs, but interactive sessions that you can work on. And this is especially useful for some of the apps that you want to use. For example, if you want to use Jupyter Notebooks or RStudio or Visual Studio Code, you can launch this as a job directly. So using all the resources that are available for you in the cluster. Here it's an example with VS Code that you launch a job, selecting the number of cores, the time that you want it to run. It will start. Please be patient, it's not instantaneous. You can connect to VS Code and start using it normally, as you will on your normal computer. Same with, I think that the next example must be Jupyter. Oh, this is VS Code. I think that it was shorter. Next example will be, as I was saying, Jupyter. Is it going to Jupyter? Yeah, it's a Jupyter notebook, same as the VS Code. You launch it as a job. You request the CPUs, the time that you need, the resources that you need, memory, and it's running as a normal job. And here you can access, for example, this is data analysis with pandas. You do your operations, run it. You can select the kernel that you need, anything that you can do normally with Jupyter. And same with RStudio. And as this, you can use lots of different apps in the same sense. Current applications, well, you have different workload managers and batch systems like Torque, PBS, Kubernetes, LSF, Slurm, or Grid Engine. And applications, I just put a few examples. I didn't put all of them, but you see Jupyter, MATLAB, RStudio, Shiny Apps, Virtual Studio Codes, Paraview, TensorBoard, whatever you need. And there are also some applications planned, like Git, Galaxy, WebMO, IBM Cloud, OpenHPC, OpenStack, and our own company is contributing to have these other applications like Determine IA, Anyscale, Nextflow, BMD, or Grafana. And that's the end of the presentation. So tēnā koutou katoa, and thank you. If you want more information about this, or you have any project that you want to discuss with us, you can contact us at this email, or talk with me, or you can talk with Guillermo here, that he will be also tomorrow in the meeting. So thank you very much.
Thank you very much. That's a very informative talk and video. Do we have any quick questions from the audience before we break for our afternoon tea?
Oh, thanks, Guillermo. I guess sometimes we have these older applications that rely on X, like, I don't know, NCView, if you've heard of it, or some other applications, and you launch the application, and then you have this window popping up, and I was wondering whether that would actually work within OpenOnDemand.
I'm not super sure. I know that sometimes we have problems, especially with some apps that use graphical interfaces, but I think that it's solvable. I think that it requires maybe a little bit more work, but in general, anything that uses a graphical interface can run on this. But I'm not super familiar with it. I'm not on the developing side. I'm more in telling users how to use it, how to do it, and so on. So probably there is somebody that uses OpenOnDemand that will know the answer, but not really me.
Excellent. Thank you very much once again, and please join me in thanking Hayam.
Thank you.